Okay, so now I want to be honest with you. I have memorized that a rectangle, where its base times height spinning around an axis parallel to the base, is 1/12 base times height cubed. I've memorized that one. I actually look up everything else. It's in a table in the back cover of your book, and I will give you a copy of this table for the exam. And when I don't have my book around, I just Google moment of inertia table, and it will pop up on Google. On occasion, I've had to do these integrals for shapes, which are not in the back cover of the book. But outside of this class or dynamics, I think I've done this less than 5 times in my entire life. What you can do is you can find this stuff in books. You just find these tables and they'll give you the centroid and the moment of inertia about both the x and the y axis. This is how you would really do it using these tables. But the real question here is, why in the world are we learning how to calculate I? Why in the world are we learning how to calculate polar moment of inertia? And you need to know these area moments of inertia for your next class, Mechanics of Materials. When you bend something, here's the formula that will tell you the stress in the member. And here's the formula that will tell you how much it will deflect. And these are, of course, very specific cases. But in both equations, you need to know this moment of inertia. When you twist something in torsion, the stress is given by this equation, and the angle that the bar will twist is given by this equation if it's a circle cross-section. And in both these equations, you need to know the polar moment of inertia. The amount of area in a cross-section will tell you how much material, so maybe how much concrete. And if you want to use the same amount of concrete but get a bigger moment of inertia, what you need to do is get all the area far from the middle. And so how would you do it? You would make shapes that look like this. There's that and that. Here you go. There's lots of area up there, area there, and this will have a high moment of inertia. Much higher moment of inertia if you took that same concrete and made a solid rectangular beam. And here's one last moment of inertia problem. These two shapes have the same area and the same centroid. They're the same triangles, just arranged differently. So here's the center, and here's the center. But this one has a lower moment of inertia, and this one has a higher moment of inertia. And I feel this is representative of what's happening nowadays. The center of what we think and what we believe, our ideas, are staying at the same centroid, but the moment of inertia is increasing, because even though we still have the same average, the individual centroids are moving farther apart. And so while these two pictures have the same centroid, the same overall centroid, the distances between the individual centroids are moving farther and farther apart. And this is kind of what I see happening in society nowadays. And so I'm hoping that somehow we can get closer back to something like this. And one very last thing, I've been using my iPad Pro to make these lectures, and the reason I'm using my iPad Pro is I can use this Apple Pencil. The iPad Pro is pretty pricey, but it was, up until recently, the only iPad that would work with the iPad Pencil, where I can draw. The new iPad that's like $330 now works with this pencil, and if you wanted to make lectures like this, you don't need this. I think this was like $1,000 to $2,000 iPad. You can get this $300 iPad to make these lectures. And I think at that price point, iPads are going to be a real force, or in Italian, forza, in the education world. And you'll see more and more lectures made with iPads.